Hello, and welcome to the Eljen GSF PowerPoint video. My name is Scott Moore. I am the Technical Development Lead for Eljen Corporation. I have been with the company for 5 years, and I am an Army veteran. The topics I will be covering today are the company history, the science behind the system, how the GSF works, GSF design options, the installation procedures, and the installation do's and don'ts. So let's start out with a little bit of company history. Eljen was founded by Joseph Glasser in 1970, where he started making prefabricated drainage product in his basement with only a few employees. In the early 1980s, we started manufacturing the GSF and got a factory in East Hartford, Connecticut. We have 100,000 systems, actually over 100,000 systems worldwide from Australia to Sweden. At Eljen Corporation, we have a tradition of hiring veterans on our technical team. As such, we work with our distributors to help out veterans across the country. This install was at Camp American Legion in Wisconsin, where we donated the product and our time to put it in the ground. Camp American Legion is located on Lake Tomahawk in Wisconsin. They have 16 cabins, all on septic systems, and any veteran is allowed to go there, stay, fish, hunt, or just relax in the location out in the woods free of charge. So we thought this was a worthy donation for us. If anybody out there knows of any veteran organization or a disabled veteran that can use a septic system but does not have the money to pay for it, please contact us and we will help out. Now let's take a look at some of the science behind the GSF. The scientific studies below show that the biological soil clogging is caused from septic tank effluent. This soil clogging will define the absorption rate. Geotextile fabric will improve the absorption rate by filtering out the solids. Sidewall and bottom area do accept effluent, and the loading rates for highly pretreated effluent are going to be different because the soil will be able to process pretreated effluent at a faster rate than it would standard septic tank effluent. This led to the development of the pilot chart. The picture below shows the basic principles behind soil clogging. Heavy loading of the soil with liquid effluent can cause soil saturation. Long-term soil saturation reduces the aerobic activity within the soil. The reduced aerobic activity prevents the natural breakdown of organic material. Suspended solids in the effluent clog the soil pore structure, reducing the long-term acceptance rate of the soil. What is biomat? Once the pore structure of the soil begins to clog and stay wet, biomat begins to develop at a faster rate. This is a naturally occurring tar-like substance, but it also processes biological solids and pathogens. When it grows to a thick barrier, it stops absorption, and then you will have a breakout and system failure. Once you have soil saturation, the only bacteria that you are relying on to break down the biomat is anaerobic bacteria. Anaerobic bacteria is similar to the bacteria working in the septic tank. It does not use oxygen. They are typically in saturated areas. They are more capable of breaking down inorganic solids than aerobic bacteria. You can see the aerobic bacteria is larger than the anaerobic bacteria. It's also better at breaking down human waste, but it does require oxygen, and it helps break down the biomat to keep it at a manageable level. If you were to look at the two bacteria under a microscope, the anaerobic bacteria might twitch, move a very little bit, but not much action, whereas the aerobic bacteria will be darting around, going back and forth, be very active. It's always looking for food and always wants to eat. That's why it's better at breaking down human waste and organic material than the anaerobic bacteria. So how does the GSF work? At Eljen, we like to explain how the GSF works by comparing it to the tidal effect on a pier pylon. Where does this pier pylon rot? They don't rot below the water level on the bottom in the sand. They don't rot up on the top where the decking is. They rot between the low and high tide level. So if you can imagine, the pylon is the geotextile fabric providing vertical surface area inside the module. When the high tide effect comes in, or when your system is dosed, it's depositing organic material on the geotextile fabric. As the effluent leaves the GSF module, it becomes an aerobic treatment zone. The aerobic bacteria go into the module and they begin to eat all the organic material, keeping the biomat at a manageable level. The geotextile fabric within the module provides surface area for filtration and biological development. This promotes biomat growth away from the soil interface, preserves the sand unit interface by minimizing clogging and promotion of unsaturated flow. Having this effluent build up on the geotextile fabric and having the module surrounded by the sand will allow the effluent to flow out at a metered rate. So if you have a really fast soil, the effluent is still going to get treatment as it goes through the module and through the sand. If you have a really tight soil, a clay or something, the effluent will flow out of the module at a rate that will not cause saturation of the soil. This geotextile fabric also provides a primary stage for treatment within the GSF module. The unique design within the GSF increases the surface area within each system. The geometry of the product is not as important as the surface area that it yields. The more surfaces increase the number of biomat growth zones, and the open air channels within the module support the aerobic activity. Rain Locke is the designer of the GSF, and he sat down one day at his desk and drew these designs on a piece of paper. And he realized that he could get more surface area inside a 3-foot wide trench by taking advantage of the open space and creating vertical surfaces on the GSF modules. The drawing below shows how biomat grows in a typical stone and pipe system. While the stone is very good at allowing effluent to flow freely through it, there is no filtration, so all the suspended solids contained within the effluent seep into the soil pores and begin to clog them. Once the soil pores on the bottom layer begin to clog, effluent rises inside the stone and pipe system and begins to clog the sidewalls. Here is a depiction of biomat growth in a GSF system. The effluent flows down through the GSF module, over the geotextile fabric, and into the sand, the C33 sand to be precise. All of the biomat is contained inside the GSF module or right below the module on the very top surface of the sand layer. The effluent that goes through the sand and into the soil is clarified effluent and looks like tap water, has no odor when it goes into the soil. This increases your long-term acceptance rate. The sand used below the GSF module is ASTM C33 sand. The ASTM C33 sand is a major component of the system, and it is the secondary treatment zone for the effluent. The requirements are less than 10% passing a 100 sieve and less than 3% passing a 200 sieve. The lack of fines in this sand make it very effective at treating effluent and not clogging the soil pores. This is just a picture of all the ASTM C33 sand specifications. If you're using a sand that has excessive fines, the fines interlock with larger particles, preventing water from moving through the sand. The wastewater will bond and the biomat will quickly grow, shutting down the system. Fines are always a killer for sand-based systems. Sand on the coarse side of the spec will allow the effluent to run out too fast and not provide adequate treatment of the effluent. The concern here is when installed close to a seasonal high water table, you could contaminate the water, or if you're in a tight soil, you could saturate that soil. You always want to use a sand that is in the middle of the high and low specification for the ASTM C33 sand. Now let's discuss the GSF design options. The minimum sizing for a GSF A42 module is 6 modules per bedroom, or 6 modules for every 150 gallons of effluent. The A42 dimensions are 7 inches thick, 2 feet wide, and 4 feet long. The white stripe you see on either end represents the top side of the module. Trench installation options are curved or straight. The picture on the left is a zigzag, and this was on a lake lot where the new homeowner tore down the old house, built a larger house, did not want to remove any trees. We were able to zigzag the system in between his driveway in the front yard and his neighbor's driveway while meeting all the setbacks. The GSF models can be installed in beds, and the mound options are straight or contoured. This is an A42 trench cross section, and you'll notice that the trench is 36 inches wide, while the A42 module is 24 inches wide. 6 inches of sand is required on either side of the modules when placed in the trench. 6 inches also goes at the very end and at the beginning of the trench rows. We also require a minimum of 6 inches of sand below the module and 12 inches of cover as measured from the top of the module. This is a trench plan view. You can see that the modules are placed end to end, lengthwise in the trench and surrounded by 6 inches of C33 sand. This is multiple trench rows where you are required to have a minimum of undisturbed native soil in between the trenches. Please refer to your county code for the distance. This one shows 6 feet. Some counties require 9 feet. Some counties require 3 feet. So please refer to the code. Here's a bed cross section, and you can see that there is no native material in between the rows, only sand. It's a minimum of 6 inches on either side of the module, so you have to have a minimum of 1 foot of sand between the modules. Typically, we center the 2 rows inside the bed. Here is the bed plan view. You can see that we have 6 inches of sand on either end of the modules as they are installed, but the 2 rows are centered inside the bed system. Now we're looking at a mound cross section. You can see we have the minimum of 12 inches of sand in between the modules because we need 6 inches on either side of each module. So it'll be 6 inches from the edges and 12 inches in between the rows. The minimum depth of sand below the modules will depend on your county code for depth to limiting layer. Usually there's a 3-to-1 slope on the sides of the modules in your mound, and depending on the slope of your site, your toe will vary. The distribution methods for the GSF system are gravity or siphon dose. You can do a pump to gravity where we like to use a D-box, or pressure distribution is allowed. When installing a pump to gravity system with a distribution box, Eljen requires that a velocity reduction pipe be installed about 2 to 3 feet before the distribution box. If the force main gets pumped directly into the distribution box, the high velocity flow into the box may force effluent down one pipe faster than another. By installing the velocity reduction, it will allow the distribution box to fill at an equal level. The dosing volumes for the A42 modules are 3 gallons per module per dose and 25 gallons per module per day. Next, we will be covering the installation. First, you must prepare the surface by cutting and removing all vegetation as close to the surface as possible. Next, we need to excavate the distribution cell. This one is a trench excavation. For a mound, we will scarify the receiving layer or chisel plow. Here is another picture of a mound with scarification. The next step is to place the C33 sand. Once the sand is placed, we need to stabilize it with the bucket of the backhoe, vibratory tamp, hand tamp, or walk it in. If we don't stabilize the sand, the first time the effluent gets distributed, the sand will find its own level and you could have an uneven system. When placing the sand, be sure not to drive over or walk on top of the scarified surface. Here's an in-ground bed with the sand placed. This picture shows the sand being placed over a chisel plowed mound. You want to make sure that you're driving over the sand. This way the sand will mix with the native soil and it'll provide an excellent transition zone for the effluent to pass through. Once the sand is in place, the modules need to be installed end to end after everything is raked level. Install the modules either in single or multiple rows. This is a mound configuration with multiple rows. Once the modules are installed, you can begin to lay out your distribution network. When you lay out the distribution network, in order to secure it, there are wire hoops provided by Eljen. Use one wire hoop over the top of the pipe on each module. To install the wire hoop, place it over the distribution pipe and press it through the module into the sand. When laying out your distribution network, make sure that the ends are capped. Eljen likes to use the pipe and pipe method for pressure distribution. So you cap the ends and use a hole saw to drill your 1.5 or 2-inch low pressure pipe hole. Vents are required on the Eljen GSF system if you have 18 inches or more of cover, or if your cover material has clay and will restrict the flow of oxygen down to the modules. You can install a shared vent for multiple rows or a vent on each row. This diagram shows one option for low pressure venting, where the low pressure pipe is run up inside of the vent. Here is another option where the installer wanted to run the low pressure pipe separate from the vent. Either one is fine with Eljen. Here is a shared vent pipe on 2 rows for a gravity system. This is a 4-row system with the vent pipe placed in the corner on a gravity system. This is fine. It can be in the middle, it can be in the corner. You can put 2, 3, 4 vents on it. 1 vent is fine. Once the distribution network is installed and secured, spread the Eljen supplied gray cover fabric evenly over the top of the modules and the distribution pipe. Let it hang down the sides. Place shovelfuls of sand or topsoil over the top of the distribution pipe so that it falls down on both sides to secure the fabric. We don't want to have any tenting. If you are throwing the sand up against the side of the pipe, you could block the distribution holes in the pipe. Once the fabric is secured on the top, bring the sand up the sides of the module so that it is even with the top edge of the module. If you have extra sand, you can throw the extra sand over the top of the modules. It will not hurt it. It will only help the system to breathe better. Once all the sand is in place, cover and seed. Now I would like to go over some installation do's and don'ts. These are just the important things to remember when performing your Eljen GSF installation. Don't install under a driveway or any surface that will restrict the flow of oxygen. Remember to remove all surface vegetation and dispose of properly. This is one option of disposing of the vegetation in your basement. Be sure to properly prepare the surface area by scarifying or chisel plowing. Always make sure when placing the sand that you do not walk in or drive on the chisel plowed or scarified surface. Always walk or drive on the sand. Place the C33 sand and stabilize with the back of the bucket. Install the modules end to end. It may be difficult to see in this picture, but the center module in there is upside down. The modules need to be installed with the white stripe up. But if you take a closer look, you can see that the module in the middle looks different. It has more open areas and less fabric showing. Here is a top and bottom view of the A42 module. You can see the white stripe painted on there. That indicates which side is up. The side on the left is the top, the side on the right is the bottom. The reason why there is a top and a bottom is we want to have the least amount of contact of the fabric to the sand. Those areas will develop more biomat because they are two wet surfaces together and will take longer to dry out. If a module is installed upside down, it is not going to fail the system, but it will develop more biomat under an upside down module than installed properly. Lay out the distribution network using one wire hoop per module to secure the pipe in place. Be sure to cap the ends, otherwise all the effluent is just going to run out on the last module and the first module. Make sure the fabric goes down the sides of the module. There will be extra fabric. Do not tuck it underneath. That will cause the same problem where the fabric will be a wet surface against the sand, which is also going to be wet, and it will develop more biomat there. Just let the fabric run out the sides and put sand in. When placing the sand on the sides of the module, make sure you have no tenting. Cover fabric that Eljen provides is high tensile strength, and it will deform your distribution pipe once you cover your system with topsoil. Make sure to bring the sand up the sides of the module to the top edge of the module. Keep the modules out of the seasonal high water table. This was not an actual install. The modules blew out of someone's yard into the lake, but it did make a good picture. The customer wanted to know if they can still use them. All they have to do is empty out the water, fish, and sand, and they're still good to use. This installer excavated the bed while it was raining, and he continued to work on the system during the rain. Then he installed the sand in the modules. It rained for the next couple of days, and it filled up like a swimming pool. If you excavate your bed or your trench or your mound and it rains and you have not put down the sand yet, you need to let it dry and re-excavate. That rainwater will seal off that system by compacting all of the area where you chisel plowed. Remove any large rocks or boulders. You can also go around. We saw we can contour or we can curve the system in the earlier slides. Then cover and seed. Divert all drainage and runoff so it doesn't go over the septic system. And please contact me with any questions. You can email me or call me. My information will be on the next slide. Thank you very much for your time. And as I said, please contact myself, Dustin Fitzpatrick, or Lance Bates if you have any questions or comments.